collimation, let's talk about different types of collimation, why we use collimation, etc. Right? And the first thing that you have to think about beam collimation, the first thing that you, the moment you hear beam collimation is you're restricting the beam. The main purpose, okay, the main purpose is radiation protection. Write it down. That should be number one thing. Garrett, move on to what we're doing right now, otherwise you're going to get lost.
I don't have this.
What do you say?
Yes, I will repeat again. The first thing that should be in your head, in your mind, okay, is everybody with me? You're not looking at old stuff anymore? Not PAM stuff anymore? Not all exams? Okay, good. So beam restricting devices, the first thing that, the number one purpose of beam restricting devices is to radiation protection. You want to minimize the exposure to the patient. You want to only include the area of interest in the image. Okay? And the main reason for it is radiation protection. Other things will come, and we're going to study them. But the first thing is radiation protection. We good? All right, now we can start. So, I'm on the objectives. I'm going to read them because they're important. Identify factors that affect the production of the scatter radiation. Remember, the enemy of your nice image is the scatter radiation. However, scatter radiation is inherent. It's there. It's there. We cannot stop scatter radiation. It's there, and so we have to deal with it. Okay? So, discuss the primary methods of radiographers use to control the scatter radiation. 2. Explain the purpose and construction of beam restricting devices. Okay? Compare the advantages and disadvantages of the various beam restricting devices. Describe the effect of beam restriction on image quality and patient dose. All right. So, let's take a look. Factors contributing to scatter radiation. What is it that affects the scatter radiation? Why do we have a lot of scatter radiation or not a lot of scatter radiation? The first thing, the first culprit here is KVP. Okay? Next is going to be the volume of irradiated material. The more tissue, the more material, parenthesis tissue, that you have to irradiate, the more scatter radiation you produce. So, someone who's overweight produces more scatter radiation than someone that is not overweight. Okay? Someone with, someone that is just normally big, okay, will create more scatter radiation than someone that is not. Okay? At the same time, also, the larger the field that you include, so you include more tissue, the more scatter radiation you're going to have. Okay? So that's why it is important to collimate. By collimating, you're restricting the amount of tissue that is being irradiated. Okay? And here's where we look at field size. You want to make the field as small as possible, medically possible. You don't want to collimate so much that you're removing anatomy that is important or pathology that will be important. Make sense? You want to include just what is necessary. You don't want to cut off important information, but at the same time, you don't want to have other stuff that shouldn't be there because it degrades your image, in addition to exposing the patient. Okay. All right. So patient thickness plays a big part. Part thickness. For example, your pelvis, your abdomen will create more scatter radiation than, say, your elbow or your wrist, simply because you have more tissue there. Okay? So let's take a look. Large field size in this case, take a look. So X-rays are going through. Some of the X-rays are going right through it. Some of the X-rays go through photoelectric interaction. Some of them go through Compton interaction, right? And Compton interaction is the problem. Okay. So when you have a thinner part, if you're comparing this and this, simply because you have a thicker part in the previous image, you're going to have more scattered radiation. Okay? Why is that? Well, because there is more interactions. You have a greater chance to interact. X-rays, photons have more chance of interacting with larger amount of atoms in a larger tissue. Okay? All right.
Yeah, it means it's a more absorption.
Huh?
It means more absorption.
More, you will have more absorption, but also you're going to have more quantum interaction. Okay? Because it's a bigger volume, it's a bigger, more atoms to interact with. Okay? Some of them you're going to have photoelectric, some of them will go through, but some of them will also go Compton. And when you have more Compton happens. Okay? All right, kilovoltage. If we think of KVP, kilovoltage affect the penetrability of the beam. So what do you do when you have a thicker part? You increase KVP, right? So you have enough penetrability, right? Okay. And what happens when we increase KVP? Okay. It affects on interactions, right? Yeah, you have more penetrability, which means more X-rays are going to go right through it. Okay. Increased transmission. That's what we call it, right? More, it'll go through, more transmission, no interaction. However, you're going to see, and pay attention here, decreased photoelectric absorption. Why? Well, if you're having more transmission, meaning that you're going to have less photoelectric. More of them are going through. Okay? At the same time, and look at this here, and I want you to underline it, and that's why I have it in red and I have it bold. Okay? All right. It will increase the appearance of quantum scatter. You're not really increasing the number of quantum scatter. If you remember when we studied X-ray interactions with tissue, I said, okay, and I hope someone still have my old recordings there. I said, okay, when you increase KVP, you decrease photoelectric absorption and you decrease quantum scatter. However, photoelectric absorption goes down even more. You absorb less and less when KVP goes up. Both of them go down, okay, but this one is going down faster than this one, than Compton. Make sense? However, let me finish. Pay attention, buddy. What happens here is that we are seeing, it appears, in your film, it appears like you have more Compton scatter because you get more scatter. And the reason why, okay, the reason why is because the scatter radiation that you're creating with the few Compton scatter have more energy. Therefore, they have more energy to reach the film. Write it down. Write it down. Everybody, write it down.
Say it again.
Yeah, I'll say it again. One last time. All right. Following here, you will see an increase of appearance in Compton scatter. What happens is, when you increase KVP, you increase transmission. Okay? Both photoelectric and Compton decrease. And so the question is, why do we see more? The reason why you're seeing more is because the very few Compton interactions that you have, because you have increased the KVP, the photons have more energy. The scatter that you create has more energy. And so you have more the energy. See, you got me. See, and so the scatter can reach the film because it has more energy as well.
Even though there's less interaction.
There is less, but they have more energy, and so they reach the film. And so that's why you see more. Okay? Good. pretty simple, but it can be confusing if you don't think about it. Even your textbook will tell you when you increase KVP, you increase Compton. That is a mistake. When you see that, cross that off. Carlton does that mistake a couple times. Not Bushel, Carlton does.
So basically, when you increase the KVP, you will see more scatter on the image. That's it.
That's it, but why?
Because they have more energy.
That's it. And so they can reach the film. With low KVP, the scatter that is created is pretty weak. Doesn't reach the film, even though you're creating more. Okay? Are everyone clear with that? Good. Sabine?
Yeah,
You're
that
good?
sounds good.
All right, excellent. All right, let's move on then. Okay, so when you increase KVP, okay, look at it. You increase patient dose. Have you heard technologists saying, "Oh, increase KVP, so we don't want to increase patient dose"? Wrong. Stay away from that tech. Okay, you increase patient dose. Why is that? When you increase KVP, okay, you increase patient dose.
You're increasing mass or intensity.
You don't have to increase
Not
mass.
mass, but then the intensity,
Why?
greater number of reactions.
Okay, come back. Yeah, Annie? You were saying? Yeah, KVP stands for kilovoltage peak.
Related to the power of stronger. It's stronger.
So,
So
if it is stronger, you have more penetration, more transmission, so you should have less. Dose, right? If you're thinking in those terms. So why is dose increasing, Garrett?
I don't know either. I don't know.
Dennis?
Not too sure.
Okay.
The energy level's higher.
Yeah, but if the energy level is higher, then you have more transmission. If you have more transmission, there is less interaction. We just said it. I mean, the previous slide, I said there is less for electrons, right? And even less content. Yes.
Is it because the electrons are hitting the target, and so there's with more force, so there's more interactions with the target, so more photons are produced?
Exactly. Exactly. That's what Christina had said. Exactly. That's what it is. Because what you're doing when you're changing KVP, what you're doing is you're changing the kinetic energy of the electrons flowing from the cathode to the anode. And that's easy to understand. You create more content. You create the X-rays that you create have more energy. But why do you have more? Why does the quantity change? Because now they can bounce to more atoms, and you end up creating more photons. Yeah.
So you're creating more photons
More
in
photons.
the target.
In the target.
Okay.
Exactly. You guys remember how was the formula? I gave you a formula for KVP and quantity.
The 15% phone?
It's in the same slide. Yeah. And remember the slide. It's in the same slide, right on top of it.
KVP and what?
KVP and quantity is the inverse. Is the inverse. So it's the square of the inverse. And so when you make changes, small changes in KVP, quantity goes up very quickly as well. Not only the energy goes up, but the quantity goes up. Okay? How about mass and quantity? directly proportional.
Yeah.
With mass is easy, right?
Yeah.
Double your mass, double the quantity. With KVP is not. KVP is, remember, is the inverse, what did I say? You divide the inverse square. Yeah, yeah, so. Are we good? All right, here we go. So decrease in photoelectric absorption, okay, additionally increasing KVP is typically accompanied by a reduction in mass. That's what you assume, if you want to maintain the same density. If you want to keep the same darkness of the film, the same darkness of the film, then what you do is you increase KVP but decrease mass. The point here is this: when you increase KVP, all right, you are increasing, okay, the amount of scattered radiation that is reaching the film, but also you're increasing the quantity, okay? And so both, KVP has the ability to increase both contrast and density. When you change mass, you only change density, no changes to contrast. But when you change KVP, both factors change: mass, density, and contrast. So this is why it's recommended to students and junior techs to stick to one factor when you're changing. Stick to one factor. Don't change both mass and KVP, because you need to get a feeling for it. Yeah, just change one. That's what is recommended. Yeah.
Isn't there some kind of new trend though that they're saying that raising KVP lowers the dose, and they're trying to do that now?
Well, yes, because with KVP, the reason why that happens. See, this is the question. It's really not a new trend. It's just, this is what they are saying. When you change KVP, okay, to maintain density, you don't have to double the KVP, okay? To maintain density with KVP, if you are within, say, 68 and 85 KVP, all you need is a change in 15%, okay? 15% is enough to double the density, but you're not doubling the exposure. With mass, to do the same, you need to double the mass, okay? Which, doubles the exposure. Okay, so that's the difference. So when you change one or the other, it's recommended to change KVP because the increase in exposure will be less than if you were increasing mass, proportional. Okay, so that's what it is. It's not that I want to reduce patient dose by increasing KVP. No. If you increase KVP and everything remains the same, mass, distance remain the same, and you increase KVP, you are increasing patient dose. However, you're not increasing it as much if you were doing the relative change in mass to acquire the same density.
So are they kind of changing their charts though, in terms of like maybe they're lowering the mass and raising the KVP on everything?
Yeah, and it's not so much because of patient radiation protection. It's more because digital systems are more sensitive to KVP changes. One small change in with CR or DR makes a big difference in your film. Okay, I keep using film in your image. Okay, all right. All right, effects on image quality. Okay, when you increase KVP, you're going to have a longer scale of contrast, which means more shades of gray. Okay, and so you're changing contrast here. Okay, at the same time, I told you before, you also change quantity, which will change what?
Contrast and density.
Quantity, just quantity straight?
Oh, and density.
Density, exactly. Good. So you can add that here if you want.
Okay.
All right. Decreasing KVP. Okay. If you decrease KVP, then also that affects interactions. What's going to happen with the interactions in this case? Don't look at your notes. Just think. What happens if you decrease KVP?
More photoelectric absorption.
And what else?
And less Compton scatter?
More Compton
More
scatter
Compton.
too.
Oh.
More Compton scatter. Okay? However, they are weaker, and so they don't reach the film
Oh, okay.
or the image detector. Okay? So, all right. So the increase in transmission, right? Increased photoelectric absorption, increased Compton scatter. Okay? Good. A few more things. Decreasing KVP, effect on patient dose, right? Yeah, decreased dose. Yeah, we agree on that. Okay? And why? Because you're going to increase photoelectric absorption. Okay, which I'll tell you in just a second. Decreasing KVP is usually accompanied by an increase in mass, which increases patient dose even more. Okay? If you want to maintain the same density. I mean, if you're to begin with, your image is lousy and will have good density, well, then you might need to increase both. Okay, but if you have a good image, and you look at the image and say, well, I have good density. Okay, then all I want to do, if I want to maintain this density, I will increase the KVP and decrease mass. Okay, so I can reduce patient dose. Okay. All right. Questions? Okay, good. One more slide and then we'll call it. Decreasing KVP also affects the image quality, and you will have a shorter scale of contrast. Okay, shorter scale of contrast is saying what?
Less shades of gray.
Fewer grays, so higher contrast, because now you have very definite differences between the black shades and the white shades. Very different. Okay? And so that's high contrast. All right, here is, it doesn't look very well. Look at it in your textbook. This came from Carlton. This came from Carlton. And take a look. It doesn't look very well here. See, this image was done, take a look, 70 kVp, 120 mass. This one was done at 80 kVp, 60 mass. This one, 90 kVp, 30 mass. Okay, I want you to look at the following. First, we're going to look at exposure. Look at the exposure we have with 120 mass, 70 kVp, 665 millirentgen. Okay, 80 kVp, 60 mass. So you cut your mass in half, you increase the kVp by 15% approximately. Look at the reduction in exposure. Okay, 120 millirengens less here. Now, if we decide to go up here, 90 kVp, 30 mass, so we cut the mass again in half, increase kVp another 15%. Look, 230 millirengens of exposure. So less exposure in each one of them. The density has pretty much been maintained. However, okay, the contrast has not been maintained. Take a look. See here, it's easier to see if you identify structures here. See, look at all of these. Can we see it here? Not really, you're losing it. See the sutures here? Okay, you see a little bit there. You don't see this one there anymore. This one you lost it. So that's the difference. Okay, you can maintain the density, however, contrast will change. Ultimately, what the question is, and that's the question that you need to ask the radiologist. What do you want? You want images that are going to look like this, you know, where it'll be easier to identify pathologies and anatomy, or you want something like this. It's a little more difficult, but look at the patient reduction. So it's up to them. The advantage with digital systems is that you can manipulate the image. Okay, and that's why, going back to what Maureen had said before about techs tending to go more higher on KVP, is because you have more ability. You reduce patient dose, but you have more ability. When you're done, I'm done.
You done?
Yeah. And so we are. So we're done. I'm sorry. Then the contrast, the changes in contrast. All right?
Okay.
Questions?
It does have pretty similar S numbers.
No, the S numbers are gonna be different because the exposure is different. But your ability to see the images are going to be,
I
are going to
I'm
be.
going to start printing up those slides here. I'll put you.
All right.